Hi, my name is Antonio, and I will be showing you guys how to do problem 2 of project 2 in this video. The objective of this is to find the roots of a user input equation, equation of the form something like 3x squared plus 2x plus 1. And those x's can be exponentiated to, however long. So let's get to it. We'll get some approximations along the way. And for the sake of time, for the sake of this software taking forever to upload to YouTube, I will just have the code written out already as not to miss my deadline. I really don't want to miss the deadline. But so here we go. We have our input, which you're going to input a row vector, some sort of row vector that will, just like I said, give you the coefficients of some equations. So like an equation like 3x squared plus 2x plus 1, the elements in that row vector would be 3 space 2 space 1. You will take the length of that row vector, save it in column. You will enter a max error that you will get for your approximation. If you get more than this error, you will your code's just not really running as it should. It should approximate a little closer, or for the user that wants that extra bit of accuracy. You need a left bound and a right bound, and you want your left bound to be less than your right bound. So here, if you enter a left bound that is equal to or greater than your right bound, you'll be asked to enter your bounds again, just to get it correctly. Once you have that, you'll your columns, your number of numbers in your row vector, and your coefficients and your left bound will get sent to function f. So let's go to function f, and really all it's doing is taking the length of not the length, it's really just wow, I cannot get the words for this. Evaluating your equation. It's evaluating your equation because you know how long it is, so you know how many x components you're going to have. You know your coefficients, which are going to be your c, your coefficients, and your x's, which are your bound. So you're going to evaluate one equation at your left bound and your right bound, and you're going to sum up everything it gives you for x cubed and x squared and x and the regular just number. You're going to add all that, and it's going to give you some y, a sum of y, and that's what you're going to output back to your main script. You're going to do that for your left and right bound. Now you're going to get a you're going to enter a while statement, or if your y's fail to differ in sign, you will enter this while statement, and you will have to input some new bounds. To get the root of an equation, you want your bounds to differ in sign, because on your y-axis, you're taking your 0. And so, of course, if your line is going up and down, or side to side, it has a slope. And if you want the intersect at 0, one of your sides is going to be negative and the other side is going to be positive, or vice versa. That's really really important to this code. So after that, you send it to a function f0, which is going to find your, oh, you don't send it to f0. f0 is a defined function already. You're going to call your left bound, and you're going to evaluate it at your f. You're going to input your f, the number that your f gives you at your left bound, and you're going to send it to your bisect root, which that is essentially all these lines of code. Well, it's not much, but these are gonna give you your bound essentially, not your bound, your zero. They're gonna give you your zero using f0 and just equating things and making sure that you're that you're in the right plane and in the right number of values of left and right bounds. That's also very important. It's going to find the iterations for which it finds your zero. Your zero. I cannot get the word zero. And it's going to output your root answer, the error that they got, and if it's, well, we'll get to this, and the number of iterations that it used. So you can come back here, and we're going to send all the same elements to your bisect root 2, which essentially is just setting it up to be plotted. You can see here, it's just setting it up to be plotted. And then once you have that, it'll tell you your approximation, or the approximation that MATLAB found of this equation, the number of iterations, the number, or the error, the maximum error that you entered, and a graph. So here we have all put in my, just a simple equation, 8x plus 5. Enter the max arrow, give it a 1, a negative 3 because my left bound has to be smaller than my right bound, and a right bound. MATLAB works, and here is my root approximation, number of iterations. And these are the, again, errors and iterations for your equation. And here in the command window, you can see that the root approximation was negative 7.5. Total of 4 iterations and a maximum error of 0.75. I'm sorry, negative 0.75 and 0.75. The graph of errors shows that this theorem is true as the graph is decreased by a factor of 1/2 to the n. I apologize for this quick and not really detailed video. This software is just really bad and takes, anywhere from 30 minutes to an hour to upload to YouTube. So, thanks for watching, and if I can explain in class if asked to. Thank you.